Alrighty, so in this video we're going to take a look at the DC Bell practical quiz because there's a few key things I want to pick up from that. So let's get started with that. So to start off with, just a few pieces of factual information that you just have to know. So a DC power supply, so that's like a cell or a battery, will produce a constant current. So depending on how much resistance we connect to it, we can change how big that is, but once it's producing a current, it will produce the same current the whole time. Whereas an AC power supply will supply a constantly changing current, so it changes both its magnitude, so the number, and also direction. So sometimes it will go left, sometimes it'll go right, depending on how it's set up in your circuit. Okay, and then so then what that looks like in terms of a current versus time graph. So a direct current, let's put it in the right one, will look like this. So the current is the same value all of the time, whereas alternating current looks like this. So it's often described as being sinusoidal, so like a sine wave. So current is increasing, then decreasing, then current is increasing and decreasing, but then in the opposite direction. Okay, so what is placed inside the coils to increase the strength of the electromagnet? So we place a soft iron core in there, and what we're going to do is explain why that is the case. So let's just quickly flip onto OneNote so I can do that. So I just want to explain what's going on here that means that this works. So essentially, here is your electromagnet without a soft iron core. So outside the coil, you see, as usual, our field lines go from north to south or north to south. That's pretty standard. So when we put a soft magnetic material inside that, the domains inside of it, which is what we're representing with the blue arrows, align with the field that is also inside the electromagnet. So you can see the field arrow and the domain arrows are pointing in the same direction, and this is what amplifies the strength of the magnetic field. You've essentially got this material is now adding on top of it its own magnetic field, and that amplifies its strength, and that can be sort of up to 1,000 times stronger. The effect of this is quite dramatic. Okay, so that's how we make it stronger. So then we're going to sketch our diagram, or circuit diagram for the DC bell, showing where the air gap forms, which is what quite a few people forgot to do on there, and then labeling our components. So let's have a look at that. So I've put the diagram next to the picture so we can identify things. So coming into power source, so I'm saying essentially in here that current goes in here, and then current comes out here. So that's why I'm showing on my circuit diagram, the current comes in and it goes straight into the arm here. So that's why I'm showing the arm, and the arm will have some resistance, which is why I'm representing it as a resistor. Then at the moment there isn't an air gap, but the air gap can form in between the arm and the nail. So the nail again has been just shown as a resistor, but the air gap can form in here. So I've actually shown that as a switch because sometimes there is an air gap, sometimes there isn't. And then what happens is the current goes in there, goes out round the back and goes into the first electromagnet. Then it goes, again, there's a wire that goes round the back that takes it to the second electromagnet. So current is not going round the iron bar. Current is going from one electromagnet to the other. And then it's coming out of the other side and back into our power supply. We've got our two diagrams for electromagnets. The lines on here just indicate that there's a soft iron core passing through them, but the current itself doesn't pass through the soft iron core. That's a key thing there. Okay, so that's our circuit diagram. Okay, so as I just mentioned, our circuit symbol for a electromagnet or a coil with a soft iron core is this one down here. Although in reality it might look like this is actually the diagram that we draw, and you can see it's much cleaner and simpler, which is why we opt for that. So which of these best describes what happens when the switch is closed? Well, as you will have seen when I played the video, essentially it produces a periodic sound because the hammer is repeatedly striking the bell, but in between it returns to its starting position, and then that whole thing repeats over again. Okay, so this one we're going to dig into quite a bit because there were some sections missing in our explanations here. So I'm going to show you what mine looks like. So we're going to explain why when the switch is closed, the hammer hits the bell. So we're not going to look at the part where the hammer is bouncing back, which quite a few of you were writing about here. We're just going to look at why does the hammer hit the bell. So the hammer being this part up here at the top, so I've just labeled that. So let's have a look at my explanation for this. So the first, I want to address a general thing, that when we want to explain why something happens in physics, we need to be thinking about resultant force. So forces are a concept we use in physics to explain why things happen. And we don't really use anything else, actually, to explain why things happen. It's forces that cause things to happen. So in terms of the starting point, we're in this diagram over here on the left hand side. So what there is there's a spring which is actually holding the arm against the nail. And what that means is we can have a current flowing. So let me actually show the nail on the diagram. Okay, so we've got the nail up here, and essentially what this means is we actually have a current. So your current goes up here and into your nail. So we've got a complete circuit, so a current flows. That's our first key thing to say. And then what we need to do is then identify, okay, so now there's a current in our electromagnet. That electromagnet produces a magnetic field. So if there isn't a current, there is no magnetic field. But now there is a current, the electromagnet has its own magnetic field. That's our second thing to say. The electromagnetic field then exerts a force on the soft magnetic material arm. So the reason the arm is attracted to the coil is it's kind of made of a material which is kind of a soft magnetic material. And soft magnetic materials, remember, are always attracted to magnets. And I put it in brackets because it's not really particularly relevant here, but it does that because its domains align with a field, similar to what we were just talking about with why it amplifies a magnetic field. Okay, so that's that. So we've now essentially got to the situation where there's a force from the electromagnet on the arm. And the reason that the arm accelerates towards the bell is that the magnetic force is greater than the tension force. So there is a resultant force towards the bell. And this is the key thing here. So in terms of explaining why anything happens, we need to talk about resultant force. So there's a resultant force towards the bell, and according to Newton's second law, a resultant force towards the bell will cause acceleration towards the bell. Because remember, Newton's second law says resultant force and acceleration are directly proportional there. So I think a good thing to do at this point would be to pause this video and turn to the additional notes section in your booklet and just note this down, because I think this is a nice illustration of how we explain things in physics. So I think it would be a good thing to write down also, so we've got an explanation of our bell. Okay, so once you've had a chance to do that, we can resume. So I'll carry on, but do pause the video and do that. So the second thing I want to explain was the next and final question. Explain why, once the hammer strikes the bell, it returns to its original position. So we're essentially going to be explaining the exact reverse of the question we just did. Because when the arm accelerates towards the bell, it breaks the connection with the nail. So again, just to give this a quick sketch, our arm is now over here. The nail hasn't moved, so our nail is now here. So essentially what that's produced is an air gap. Okay, so we've broken the connection with the nail. So there's a massive air gap. Air has a massive resistance, so there's no longer a current in the circuit. You might occasionally see when they're a bit close together, you can sometimes get sparks jumping the gap, but you need a very narrow gap for that to happen. So if there's no current in the circuit, the electromagnet no longer has a magnetic field. And since the electromagnet has no magnetic field, there's no longer a magnetic force, or a Lorentz force if you like, on the arm. So now we're in a situation where the resultant force is now in the opposite direction. So in my diagram, that means it's now to the left, because only the spring is still acting on it. So that we can put our spring back in. So we've got a spring in here, and that's exerting a force to the left on the arm because the spring is trying to unstretch itself. And according to Newton's second law, if there's a resultant force, in this case to the left, it will accelerate to the left away from the bell. It will reconnect with the nail, and then the whole process can repeat over. So that's our explanation for why the hammer returns to its original position once the hammer has struck the bell.